All right, so I figured I would talk about a subject that comes up a lot, or well, a lot. I don't know. When it comes to making applications in Haskell and so on, there are a few things that are fairly common, but are not necessarily kind of obvious when you jump into it and so on. And so today we're going to talk about the reader monad and IO and how they can sort of work together to be sort of the basis of how you do stuff. And then also how you kind of abstract away from that to a place where you can pretty confidently say what a function kind of has access to in terms of what it can do and so on. So first, let's look at RIO as a concept, what it represents and how that works. Not internally, but what it sort of does for you, right? So we start every application in Haskell from main in this main function. Main has the type IO unit, always. And usually what we do somewhere along the line in applications, many applications at the very least, certainly not all of them, but many, is that we will basically transfer into a bigger monad in a way, right? A monad that represents some additional capability. And for many of these applications, that monad is going to be real or an equivalent of some kind. It could be reader together with other stuff and so on, so forth. So we're going to look at what that means. If we go to run here, let's see, hang on, run, we can see that we still have this type, IO of unit. This is really just a choice made for this application, nothing super interesting about that. If we look at add migration, we can actually see that this still has the type IO of unit, but there's a small difference here with some of the other ones. For most of the commands here, we actually do a thing called, we do something here, run RIO is what we call here, with an app. And then we execute some kind of command. This command here is going to be a RIO action. And what that means is really just, this is a value that basically represents something to do in RIO, right? So you can view this the same as we would view an IO action, right? When you execute this action, you're going to get some result out of it, and there could be effectful things happening, right? And what RIO actually is, right, is reader on top of IO. So reader, the reader monad, and the reader T monad transformer, you layer this on top of another monad in order to give it the capability to read an implicit value, right, of some type. So what that actually looks like, if we go to here, let's just look at reader T. Reader T here, if we go to the definition of this, has some kind of environment R here that we can read. It on top of some monad M, and it returns some value A when you execute it. So we have this run reader T, which you give it an environment, and then it will give this M of A when you run this. Likewise, we have run RIO, which when you give it this environment, you give it an action, will give you IO of a value, right? So reader T here, if we go to RIO, we can actually go to this very specific here. This is the reader plus IO monad, right? It is on top of, you can view this conceptually as being on top of IO, which means it provides the capability to read a value, and it provides the capability to execute IO actions. And that's it, right? From this, we get kind of a design pattern that makes a lot of sense. So let's look at a practical example of this, right? Here we have run RIO app, right? The environment that we're providing to these functions is app, right? So RIO app, if we go to one of these functions, we'll see RIO app. This is the actual monad, the context we're executing in. This means the only thing this signature says right now is in this function, we can read an app value. That's it, right? So for this, we can basically say, okay, that means we have access to an app value, right? So what is in the app value? We have a log func, logging function, process context. Some of these are just standard things. We have the options that were passed to the application. We don't really need this in our app, but it's there. We also have an SQL pool, right? So implicitly, when you have RIO app, you also have access to these things, which means this is the reason we actually can execute SQL queries. If I were to somehow remove this, and we don't have a parse error here, actually let's remove both of those and see what happens here. This function here right now says you don't have a PostgreSQL pool. You cannot call runDB. Your environment here does not have this. So as soon as someone removes the SQL pool here from our application, we no longer can execute DB actions. This is implicit, right? So this gives you a design kind of pattern here where you can essentially say, well, I have a bag of handles to things like SQL pools, file handles, and so on. These are things we cannot actually we can't keep passing this around in our application, but we can put it in a kind of global state with references to things. And this seems maybe unhygienic or whatever to a lot of people, but this is in effect probably one of the simplest ways to do things in reality, right? And I don't view this as a bad thing. Holding an SQL pool, yeah, this is just how it is. An SQL database is just one big ball of mutable state. There's nothing we can do to make that nicer. We could try to have a different type of database, but fundamentally this is a reference to a mutable, very large file. We can change parts of that file, right? And that's it. That's how it is. So we have this pool in our state. Better than that though, we can also define these type classes that sort of say, if you have some piece of data, we can describe what it means to have a PostgreSQL pool. And we saw that this was actually part of, when I deleted code here, we saw that this stopped working, right? So our other function stopped working because we didn't have this here. This here stopped working, right? So from this kind of design pattern, we get a few nice things. And I'm going to illustrate sort of how we can take this to a point where we can actually kind of see much more clearly what is actually happening in a lot of these functions. So let's take one of these and sort of convert it to a new style, right? Right now we have RIO app, right? And that's fine. I'm not trying to say that it's not, right? But let's say we want to kind of make it clearer what this function is actually kind of doing. And we might actually learn something about our functions along the way. So the first thing we do is we generalize the monad type. This type here basically now says, well, this returns some m, right, of unit. And this is not going to work here. We're going to immediately get an error. No instance for monad m. So let's say monad m could not deduce monad throw. Okay, monad throw m. And monad throw also implies monad m. So we can remove that one. Monad IO. has PostgreSQL pool. And so here, I'm going to add has PostgreSQL pool plus the methods here on that class. And we're still going to have to add this. And the interesting thing about has PostgreSQL pool here is it needs some kind of environment in a reader monad. And so here's where we actually generalize over reader monads. So RIO, we said, was a reader monad because it implements this kind of behavior, right? And what we're going to do here is say this monad reader env m. And then I'm going to add has, well, first let's say this, right? Has PostgreSQL pool env is what we're missing. So now we've basically said all of it in one go. And we can first of all be completely certain that we've described what this function can do so far as we have type classes describe the behavior of these functions, right? So we have a reader, which means we provide implicit values. We saw this already with RIO, as long as we understand what RIO means. We can actually see now that this has something that explicitly throws. We couldn't see this in our type before, right? Monad IO we could see because RIO has IO. But we can also see now this uses PostgreSQL pool. Of course, migrate all kind of suggests that we are, right? But we can see very specifically this requires that. And if someone does remove this, well, they can't. We can't execute the function if that happens. So now we've basically made it completely clear this is what this function does. So if we do this with the others, right, we can actually kind of copy part of this. Here we can see redundant constraint. Haskell is telling me you don't need monad throw here. I don't know what you're talking about. So this works also the other way, right? When you stop using certain functions, Haskell will no longer think that, well, this is required, right? I'm skipping over, of course, IO here. But the truth is, if we did M here, we could say monad IO M. And there you go. So now basically this is equivalent to that other one, except this function now also executes in any monad IO monad. So anything that implements monad IO, RIO, for example, or reader T on top of IO, for example. So we've now just made it slightly more general, but it has the same capabilities, right? So let's just continue doing this for all of these, right? We can just say monad IO M, probably, you probably need that one. Monad throw, okay. Monad reader. And here we're gonna need the PostgreSQL pool env. And there you go. And really, this is almost, it's almost a mechanical transformation for if you just follow kind of the breadcrumbs, right? And here we definitely need monad reader and M. And we can just keep going like this. Actually, here we maybe don't need IO. Let's see. Oh, read in. That's not the correct thing. Yeah, we need monad IO. And that's it. Here we can actually see a function that already was like this. Mostly that's because, yeah, this is a reasonable way to do things. To be honest, if you have library functionality, this is certainly the way to do things, because that way your function will fit into any environment that provides these things. So if we look at remove migration now, for example, or migrate all, for example, right? This will now work with any monad that implements all of these, right? So it needs to be able to throw, it needs to have access to IO, it needs to have a reader environment that it provides. That environment also needs to have a PostgreSQL pool. Our function is now maximally reusable for any monad that has those capabilities. right? So I think this is generally a good way to do things. Certainly you can overdo it. But you'll also kind of, in some way, if you find yourself putting a lot of these things in a function, you might consider, one, am I being too fine-grained with my capabilities, right? So do I have like 15 of these for every function? Well, in that case, maybe you can bunch a few of them up, because I'm sure there are patterns here, right? But also, to some degree, you can kind of accept that when we have a lot of these in one function, it means that function does a lot, right? And certainly, it's clearer still if we're having issues reading from the database, for example, and we have these type classes, for example, that might say monad read db, or just read database or read db. It might be a good idea to have these annotations in the type classes and so on, because when we are debugging reading of certain types of values, for example, we can nail down which functions could be having this issue, which function is causing this issue. Where could this happen, right? It immediately narrows down stuff, right? And I think in general, this kind of problem of not really, it's a very common problem in my experience, that a code base can evolve in such a way where people do random things in random places, unless there's something to kind of nail things down. And this is a very easy way to combat that. It is very convenient to be able to look at a function in isolation and be able to say, here's what this can do. It literally cannot do anything else, right? If I were to try to do something else here and so on, than these things, it just wouldn't allow me, right? Even better if you don't have monad IO, because IO is of course like a license to do almost anything. So from that perspective, this is not as useful as it could be. If we kind of nail down things to the point where we even can remove monad IO, we actually we reach a situation where it becomes fairly obvious that, wow, this function is so nailed down. It has such a clear interface, right? Because here we could still just say lift IO, write everything to a file onto disk, and email it to someone. We have access to a lot of stuff when we use monad IO like this, right? So it can be worth it, I think, to some degree, in a code base where you have very clear restrictions for which part does what, to actually not allow this kind of thing, not have monad IO like this. You can put it behind another interface instead, and just sort of have that interface be the one that's used, which will give access to only certain things. We might look at how you implement these things at some point, right? Right now, I just want to show kind of what this means for our functions, right? So if we look at this from this perspective here, we started with this up here. We ended up with this monad reader, env, monad throw, etc., right? Lots more information here, right? A lot more information in these type signatures. So yeah, that's basically what I wanted to show today. And again, we're gonna look at some point at what does it mean to implement these, so that we can sort of factor out these kinds of interesting things, these effects, right, in our functions, right? And not with some high-flying stuff, but rather fairly a la carte, fairly basic, very simple, and scalable to a large degree. But yeah, okay. That's it for today, and I will see you some other day. Ciao.